So far we have seen the operation of a DC to AC inverter in different switching methods, and we also looked at the current waveforms and voltage waveforms at the output. And all this has been done by generic switches. We have represented by a single pole single throw switch. But how do we realize an inverter in practice? For that, as we have done in the case of DC to DC converters, we need to look at the voltage blocking capability and the current carrying capability required for each switch. Let us take a look at the same. When S1 is on, what is the current flowing through S1? IS1 is equal to IAB, and IAB is the load current. If it is an RL load, as is the case in most applications, we also have seen in the previous example, the current could be something like this first waveform or second waveform or third waveform. But however, it has both positive and negative values. That is what is important to us. So S1 should be capable of conducting in either direction, in any direction, because it is not necessary that whenever S1 is on, the current IAB should be on or something like that. Why? Because the direction of current, in fact the polarity of current IAB, whether it is positive or negative, it depends upon the characteristic of the load. So consider the RL circuit, the load as RL, and VAB has components omega 1, omega 2 and so on. Omega 1 is the fundamental component, omega 2 is the next harmonic component, it's not the second harmonic, of course. So as we have seen, the immediate harmonic component is at very high frequency, so the current is dominated by the fundamental component. And how does a current fundamental component look like? It will look like this purple colored waveform shown. It will be lagging VAB1. Why? Because it's an RL circuit, and the angle by which the fundamental component of IAB lags VAB1 is simply tan inverse omega 1 L by R. And what is this omega 1? Omega 1 is the frequency of the modulating signal, MA. Omega 1 is the frequency of modulating signal. So this is Vm sin omega 1t, right? So, and MA is going to decide whether S1 is turned on or S4 is turned on. So when we command S1 to turn on or S4 to turn on, whether the current flow is upwards or downwards in S1 or S4, it is not in our hand. It is in the load's hand. The load will decide, because the load has inductive nature. So S1 should have a bidirectional current carrying capability, and same is true with all the other switches, S3, S2, S4. And how about the voltage blocking capability? When S1 is off, what is the voltage across the switch? VS1. VS1 is equal to VDC, because whenever S1 is off, S4 is on, because current IAB has to flow, so that cannot be interrupted. So whenever S1 is off, S4 will be on, and because S4 is on, the voltage across S1 VS1 is simply VDC, and VDC is positive always. So S1 should be capable of blocking only positive voltage, and same is true with all the other switches, S2, S3 and S4. So S1 should have bidirectional current carrying capability and unidirectional voltage blocking capability. So naturally S1 can be replaced by a MOSFET, which already has an anti-parallel diode, or which is known as body diode within the structure. So MOSFET is shown here, which can easily replace the switch S1 for practical implementation. And when the blocking voltages are a few hundred, more than a few hundred, up to a few thousand, and even the currents that need to be carried by the switch go more than a few hundred amperes, people even more than a few tens of amperes onwards, all the way up to a few kiloampere, people go for IGBTs, which are shown here. But an IGBT doesn't have a natural property of carrying current in both directions. So we need to attach a diode anti-parallel with IGBT. So now the current can flow through the IGBT or the diode, but the voltage can be blocked by the diode or the IGBT. If you don't give a gate pulse, IGBT will also be able to block the voltage, or the diode can naturally block positive voltage with this polarity. That means negative for the diode, right? So a real DC to AC inverter circuit using IGBTs is shown here, and each switch can be replaced by an IGBT with anti-parallel diode or a MOSFET which already has an anti-parallel diode in a similar manner, and that results in this circuit. This is a very well known circuit and used widely in many applications. So we have realized a single phase DC to AC inverter using 4 IGBTs and 4 diodes. But which of them will actually conduct at any given instant? How do we determine which switch is conducting? For that we need to look at both voltage and current waveforms of the load, the voltage across the load and current through the load, that is VAB and IAB. Let us consider the simplest case of square wave operation. So in square wave operation, if the load is RL, then the current will exponentially rise and will exponentially fall, and the time of fall or time of rise will depend upon the time constant RL. We have also seen this kind of waveform in the examples shown earlier. And of course VAB, since VAB does not have zero average value, IAB will also not have zero average value in steady state. So we are looking at periodic steady state. So in periodic steady state, at this instant, at this particular instant, the current will start at a negative value. The current will start at negative value because it would have been negative here. Now in periodic steady state, let us look at the first interval. And what is that? That is this interval, this particular interval. In this first interval, in the very beginning of this interval, VAB has to become positive. Earlier VAB was negative. Now VAB has to become positive. That means top switch of leg A and bottom switch of leg B should be turned on. But IAB is still negative. The IAB will become positive, but it will take some time. It has that exponential rise. So IAB will still be negative in this particular interval. Since VAB has to be positive and IAB is negative, the only switches that can conduct are D1 and D2, because current has to flow in the opposite direction of IAB, that is indicated here. So current flows through D2 and flows through the load and flows through D1 and reaches back the DC source. But the voltage VAB is definitely positive. Why? Because A is connected to the top and B is connected to the bottom. A is connected to the positive DC terminal and B is connected to the negative DC terminal. So the voltage across the load is positive, but the current flowing through the load is negative. Now coming to the second interval. This is second interval. VAB is greater than 0, has to be greater than 0, and IAB now has become positive. Then what will happen? S1 will conduct and the current flows through S1, load, and S2 and goes back to the source. Similarly, in the negative half cycle, the beginning of negative half cycle, there is an interval in which the load voltage is negative. The load voltage is negative. That means top switch of B leg should be conducting and bottom switch of A leg should be conducting. That means A should be tied to this point, the negative of DC bus, B should be tied to the positive of DC bus. But the current is still positive, IAB is still positive. So D3 and D4 are the devices which conduct in this interval, because current flows through D4 and through the load and D3 and back to the source. So that is how the positive current is maintained. But as soon as the current becomes negative, S3 and S4 will take over. So S3 will start conducting in downward direction and current flows through the load in a negative direction. Then it goes back, it comes through S4 and goes back to the source. So this is how we determine the actual switch. We identify the actual switch that is conducting at any given instant. The interesting point to note here is that in these two intervals, this interval and this interval, even though we give a pulse to IGBT, its anti-parallel diode will conduct because current is in the other direction. But that current direction is decided by load. That is an interesting point to note here. And how is this identification of the switch which actually conducts, how will this be helpful? It will be helpful to calculate the conduction loss. Because we need to know the exact interval in which a device is conducting. So that has to be found using this method. In addition to the main circuitry, any inverter will have some more circuits which are essential for its operation. For example, there is something called gate drive circuit which is indispensable, and it's a most crucial part of any inverter circuit. In fact, any power electronic circuit, if you have fully controlled switch, you need to have a circuitry which will control the gate. It will apply a positive voltage across the gate in the case of MOSFET and IGBT so that they turn on. So if you observe here, the two gate drive circuits that are needed to turn on two IGBTs will have different grounds, because the current completes through different terminals, different reference terminals in both cases. So that brings in the need of isolated power supplies. That means power supplies with isolated ground, which we discussed while discussing the flyback converter. And what is the input to this gate drive circuit? The input to this gate drive circuit is typically the pulses, the turn on, turn off pulses. And where do these pulses come from? These pulses come from some kind of analog or digital controller, and basically analog circuit or some digital circuit. And what is this analog circuit? The analog circuits are typically op-amp based. For example, you want to do sine triangle PWM, you will have a sine wave generator based on op-amp, and you will have a triangular wave generator based on op-amp, and you have a comparator again based on op-amp, which will compare the sine and triangle and generate pulses, and those pulses are given to this gate drive circuit. That is one way which is done in an analog manner. Over the past decade or so, digital controllers have become more popular. So we have DSP processors, we have microcontrollers, and we have FPGAs, field programmable gate arrays. So these circuits, these processors can be programmed in embedded C or VHDL, some kind of language, and you have a sine wave generation function that can be defined, and you have a triangular wave generation, and those two can be compared within the processor itself. And finally the pulses come out through the digital input output pins, the digital IO pins of these digital processors, which can directly be given to the gate drive circuitry. So this gate drive circuitry is an indispensable part. And also there are some protection circuits. So one might want to have a protection against overcurrent, or a protection against short circuit, or a protection against over voltage or under voltage. So these kind of protection circuits are also used to build a complete inverter circuit in many applications.